Welcome to This Explainer. I'm Rusty Flint, I'm a massive quantum science nerd, and today I'm going to be your personal guide into the weird, wild, and absolutely wonderful quantum realm. So, our goal right now? We're going to demystify quantum computing for you. Zero confusing math jargon, I promise. Look, imagine you're trying to find your way out of a massive maze. A regular computer, it tries every single path, one by one, until it finally finds the exit. But a quantum computer? It looks at every single path all at the exact same time. It's wild. We're going to break down exactly how this is possible, how it works, and why it is literally going to change everything. We are standing at the edge of a technological revolution, my friends. We are essentially stepping into the 1950s of the future. 10 septillion years. Guys, that's a 1 followed by 25 zeros. To put that into perspective, the universe itself is only about 13.8 billion years old. So this number represents exactly how long it would take a traditional classical computer to solve one specific, highly complex mathematical task. It's essentially an impossible amount of time, like we'd be waiting forever. Okay, let's dive into this right now. Here we have Frontier. It's the world's absolute fastest classical supercomputer. As we just talked about, it would take Frontier 10 septillion years to complete a specific, incredibly complex benchmark test. Now, put that up against Google's new quantum chip. It's called Willow. Willow recently completed that exact same unfathomable task in just 5 minutes. Yep, 5 minutes versus the lifespan of literally trillions of universes. That's not just a speed boost, right? That is a fundamental demonstration of computational complexity that our current binary computers simply can never, ever replicate. No way.
Section 1. Qubits explained. Beyond ones and zeros.
So how on earth is that massive leap in processing power even possible? Well, it all comes down to the foundational difference between the computers we use every single day, like, the phone in your pocket or the laptop on your desk, and these new machines. See, a classical computer uses what we call bits, which are honestly a lot like light switches. They can only be either off, representing a 0, or on, representing a 1. It's one or the other. But a quantum computer uses qubits. Because of this mind-bending quantum mechanics principle called superposition, a qubit can be a 0, a 1, or entirely both at the exact same time. Think of a regular bit like a coin sitting flat on a table. It's definitively heads or tails. But a qubit? It's like a coin spinning in the air. While it's spinning, it is this blur of both heads and tails simultaneously. And it's this exact ability to exist in multiple states at once that creates this exponential parallel processing power. To really anchor this kind of abstract physics concept to a staggering reality, let's just look at the unbelievable scale of this quantum potential. Because qubits can exist in these multiple states at once, their power grows exponentially with every single qubit you add. Get this, if you have a quantum computer with just 300 perfect qubits, it can theoretically represent more computational states at exactly the same time than there are atoms in the entire observable universe. Seriously, just 300 of them. It completely shatters our traditional understanding of computing limits.
Now, the second magic trick of quantum mechanics is entanglement. This is a phenomenon where 2 or more qubits become mysteriously linked together. When they're entangled, whatever happens to one qubit instantly affects the other one, even if they're physically separated by just vast, vast distances. Albert Einstein actually famously called this spooky action at a distance, which is pretty spot on. In a quantum computer, these entangled qubits work together in this coordinated, almost telepathic dance. They share information instantly, and that's what allows the whole system to speed up complex problem-solving incredibly fast.
So I've got to ask you, how do you actually build a machine that can wrangle spinning coins and telepathic atoms? I mean, it's one thing to talk about theoretical physics on a chalkboard, right? But how do we transition into the actual mind-bending reality of hardware engineering? Because as you can probably guess, keeping these qubits stable so they don't just lose their magical quantum properties is incredibly difficult.
Section 2. Extreme environments. Colder than outer space.
To keep these incredibly fragile quantum states stable and prevent them from collapsing back into just boring classical ones and zeros, which, by the way, is a process called decoherence, engineers have to build machines that look straight out of science fiction. There is no single right way to build a quantum computer right now. One really popular method is superconducting qubits, which are used by folks like IBM and Google. These things have to be chilled down in massive dilution refrigerators to about 15 millikelvin. That is a tiny fraction of a degree above absolute zero. It makes them literally colder than the vacuum of deep space. Then you've got trapped ion systems, like those from quantinuum, which hold individual charged atoms in place using electromagnetic fields. They manipulate them with lasers inside room temperature vacuums. And, we even have photonic systems that use actual particles of light to process information at the speed of light. It's wild. We're watching a fascinating hardware race unfold in real time.
Section 3. Real-world applications. Solving the unsolvable.
Okay, it's time to shift our focus to why this actually matters for you and me. Because quantum computers, they're not just going to make your video games load faster. They are going to solve the unsolvable. Massive global industries are already actively testing hybrid quantum systems. In pharmaceuticals, companies are partnering with tech giants to simulate how proteins fold at a molecular level, something classical computers struggle heavily with, all to discover life-saving drugs way faster. Financial institutions like JP Morgan, they're testing them to optimize incredibly complex market portfolios. Logistics teams are benchmarking routing algorithms for global shipping, and engineers are using them to discover entirely new classes of advanced materials. It's a total game changer.
And this brilliantly illustrates the real-world impact right here. Boeing recently launched their $2.5 million QUIC project. They're applying hybrid quantum classical computing to model aircraft corrosion right down to the molecular level. Think about that. They aren't just waiting around for a perfect quantum computer 50 years from now. They're using quantum-inspired platforms today to figure out exactly how materials degrade so they can build safer, longer-lasting airplanes for all of us.
Section 4. The security threat, quantum decryption.
Now, we do have to impartially address the elephant in the room. With great computational power comes a massive, massive threat to modern cybersecurity. This is known in the security world as the harvest now, decrypt later strategy. For absolute beginners, here is exactly how hackers are operating right now. Step 1. Adversaries steal massive troves of highly sensitive encrypted data today. They can't read it yet, but they just store it. Step 2, they wait for quantum hardware to mature over the next decade or so. And step 3, once the machines are powerful enough, they use them to crack the encryption and read the data they stole years ago. This means the threat isn't just a future problem, right? The threat to your data is happening today.
But hey, don't panic. The world's top scientists and security experts haven't just been sitting around waiting for the sky to fall. The National Institute of Standards and Technology, or NIST, has already finalized brand new post-quantum cryptography, or PQC standards. These are entirely new, quantum-resistant algorithms. Basically, they're math puzzles so incredibly complex that even a fully powered quantum computer can't solve them. Governments and major tech companies are already deploying these new defenses right now to protect our data before the quantum hardware fully arrives. So, we're getting ahead of it.
Section 5. Welcome to the 1950s, the quantum infancy.
I really want us to zoom out for a second and look at exactly where we stand in the grand historical timeline of this revolution. I firmly believe this. We are in the 1950s quantum equivalent of the classical computing world. I mean, think about the classical computers of the 1950s, the ENIACs, right? Those massive machines that took up entire warehouse floors just to do basic calculations with glass vacuum tubes. We look back at them now with a smile, knowing they eventually shrunk down and became the smartphones in our pockets. We are at that exact same magical, awe-inspiring infancy stage with quantum computing today. We are literally watching reality-altering technology take its very first steps.
So I want to leave you with this final, exciting thought. We've talked about what quantum computers are, how they use superposition and entanglement, and the absolutely incredible real-world problems they're starting to solve. But the true limits? They are entirely unknown. As this hardware shrinks, scales, and eventually becomes accessible to the entire world, what will you build when the quantum future finally arrives? Stay curious, my friends, and keep exploring the quantum realm.